Hello everyone, my name is Nicholas Barron, and today I'm going to talk about the false positives and false negatives of the Jacobian matrix and kinematically redundant parallel mechanisms. So to begin with, I'm going to give a brief introduction, followed by a description of the rigidity matrix in parallel robots, and then I'm going to talk about kinematic redundancy in parallel robots, followed by the method of computing the Jacobian for these mechanisms. And then following this, we can look at some of the limitations of using the Jacobian as a basis for singularity analysis. And then finally, a discussion and conclusions will be drawn. So as many may know, the Jacobian matrix is a popular tool for performing the singularity analysis of parallel mechanisms. And this is normally formulated in terms of finding the relationship between the velocity vector of the end effector, given here by x dot, and the velocity vector of the input actuator joints, here, given here by theta dot. And we formulate this relationship in terms of the Jacobian matrices A and B. And traditionally, three classes of singularity are defined on this basis when each and both of A and B are singular. So the first type of singularity, which is called the inverse kinematic singularity, occurs when matrix B is singular. And physically, this corresponds to a configuration of the mechanism where the mechanism loses a degree of freedom. For example, the end effector may have reached the edge of its workspace. And this type of singularity can occur for both serial and parallel mechanisms. However, the second type of singularity, the four-kinematic singularity, occurs when A is singular. This refers to a type of singularity where the mechanism gains an additional degree of freedom instantaneously. And this type of singularity is specific to parallel mechanisms and indeed is extremely problematic because it can cause a loss of control of the mechanism. And finally, the third type is simply when both of these instances occur at the same time. But as said, the most problematic type of singularity for parallel mechanisms is indeed the four-kinematic singularity, because the end effector instantaneously gains a degree of freedom, which can lead to a loss of control of the robot. And to give a quick intuition about the geometric conditions which can lead to this, we have a simple 3 degree of freedom planar parallel mechanism here. And we will see that the conditions for entering a singularity is when the lines drawn through each of the 3 limbs all intersect at a common point. And here we've entered the singularity and the mechanism has lost its rigidity. The mechanism may experience some shaking of the end effector, for example. So Jacobian-based methods of singularity analysis have seldom been queried, and here it is shown that they can actually be unreliable when applied to kinematically redundant architectures. The Jacobian is shown here to both incorrectly identify singularities in the mechanism's workspace. We call this a false positive case, and fail to identify singularities as well. This we term a false negative case of the Jacobian. And this is verified using the principle of rigidity theory as a steadfast method to determine if the mechanism is rigid or not in a particular configuration, and therefore it's a steadfast method of determining if we are in a singularity or not. So here we are going to go quickly through the method of computing the rigidity matrix of a parallel mechanism. First of all, we form the corresponding graph of the mechanism by forming the vertices of the graph in terms of the position of the joint centers, and the links and the edges of the graph correspond to the links of the mechanism. And then each row of the rigidity matrix corresponds to an edge, and each column corresponds to a coordinate of a particular vertex. And then each element in the matrix is determined if that element is in a row corresponding to a particular edge, and is in a column which corresponds to the coordinate of a vertex which is part of that edge. And then the value of the element is computed by determining the difference between the 2 vertices in that edge in terms of the coordinate dictated by that column. So we have an example here. We have a very simple parallel mechanism consisting of 3 revolute joints, and we have the corresponding rigidity matrix for this mechanism below. So this is how to compute the rigidity matrix. And once we've done this, we can determine if a configuration of a mechanism is rigid or not by computing the total number of allowed motions of the framework, which is given by the formula on the screen. And this is given in terms of the number of vertices and the dimensionality of the space. And then a framework is rigid if and only if the rank of the rigidity matrix is equal to this value S. So to summarize, we determine if a configuration is rigid, is in a singularity or not, by firstly computing the rigidity matrix, then determining its rank, and then comparing this to this value S. And if it drops below this value S, we know we've entered the singularity and we've lost rigidity of the mechanism. So kinematic redundancy in parallel robots. A parallel robot is kinematically redundant if the number of actuated degrees of freedom exceeds the number of degrees of freedom of the end effector, but is equal to the total number of degrees of freedom of the system. So in other words, the number of actuated joints is greater than the degrees of freedom of the end effector, but all the actuated joints are required to be locked in order for the mechanism to be rigid. So we have 3 examples on the screen here of kinematically redundant parallel robots. But what's interesting about these 3 in particular is that none of them exhibit actuator joints connected in series. They all use prismatic actuators here, but none of them are connected in series, which is not the case for all kinematically redundant robots. It's common that you make the robot by having actuator joints connected in series. However, this brings the problem of accumulation of actuator joint errors along each limb, whereas these mechanisms here do not exhibit this problem. And it is these types of architectures which we're going to perform the analysis on today. So let's consider the first mechanism. Here we have the planar kinematically redundant mechanism, and we're going to compute the Jacobian for this. And so firstly, we formulate the relationship between the output velocity vector of the end effector, given here by c dot, and the input velocity vector of the actuator prismatic joints, given here by q dot. And so c dot is a 3-dimensional vector because the end effector is undergoing planar motion, and q dot is a 4-dimensional vector because we have 4 prismatic actuated joints. And this means that the Jacobian matrices J and K are 3x3 and 3x4 matrices respectively. So we determine this matrix, this equation, by first of all forming the vector loop equations you see on the screen here, which relate the base of the mechanism to the end effector of the mechanism. And we see here, like if we consider the first equation, we can see the equation relates the velocity of the end effector given by PE dot to the velocity of the prismatic actuated joint given by rho 1 dot. And a similar relationship occurs for each of the other 3 equations. Now, traditionally for computing the Jacobian of non-redundant robots, we would simply, the Jacobian would simply be formed by each of these individual equations being used to form an individual row of the Jacobian. However, this cannot be done here because we have 4 equations, whereas the Jacobian only consists of 3 rows. Therefore, we need to combine 2 of these equations to form one of the rows of the Jacobian. And in this case, the last 2 equations on the screen need to be combined in order to form this 3rd row of the Jacobian. And the way we do this for this specific mechanism is by utilizing the fact that joints P3, P4, and P5 are all part of the same rigid body. This means a relationship between the vector from P3 to P4, given here by P3, 4, and P3, 5 can be related with a constant relationship. And taking this derivative of this relationship, we can combine those 2 last equations on the previous slide into one expression, which is the second expression you see on the slide here. Once we do that, we can make P35 dot the subject of this expression by taking a matrix inverse. And the matrix inverse you see here is given by the value n. And then once we've done this, we can substitute P35 dot back into one of the initial equations, and then this forms the 3rd row of the Jacobian. So this was a very brief summary of how to compute the Jacobian for this mechanism. But the key takeaway here I want to emphasize is that we needed to perform a matrix inverse in order to eliminate a redundant variable. And that's how we formulated the third row of the Jacobian. So now let's consider an instance where this causes some problems. So we have a particular configuration of the mechanism here with the set of joint coordinates put at the bottom of the screen. And if we compute the Jacobian of this configuration using the method just described, we will find that the Jacobian is singular. If we compute its determinant, it's equal to 0. However, the robot is not in a singularity. And we can verify this by computing the rigidity matrix of the mechanism and computing its rank. And indeed, if we do this, the rigidity matrix is of full rank, which means that this is a rigid configuration of the mechanism. Therefore, it's not in a singularity. So we term this a false positive case of the Jacobian, because the Jacobian says we're in a singularity when we are in fact not. So now we're going to look at a false negative situation of the Jacobian and consider here the spatial architecture presented earlier in the presentation. This architecture is going to undergo a trajectory where it moves into a singularity. And in this case, that is where two adjacent links become collinear. And indeed, we know this is a singularity because if we could compute the rigidity matrix and determine its rank, the rank drops when we move into this configuration. But however, if we compute the inverse of the condition number of the Jacobian of this mechanism, we will see that it does not approach 0 as we move towards this singularity, which is this pose you see on the screen right here. Whereas normally, the Jacobian should correctly identify the singularity by saying that the inverse of the condition number is equal to 0. However, it is not done this here. So we call this a false negative. The Jacobian has failed to identify a singularity. So to summarize, the issues with the Jacobian have serious implications for path planning algorithms for kinematically redundant parallel robots. And these issues arise from the need to eliminate redundant variables when computing the Jacobian. So to go back to the Jacobian of the first planar mechanism, we have here the method of computing the third row of the Jacobian is to compute this matrix inverse, which is given by the value n. And the false positive case of the singularity shown earlier actually occurred because this matrix, this submatrix n, itself became singular in the configuration, which caused the Jacobian to say we're in a singularity. However, this does not correspond to any physical meaning because the mechanism is in a rigid configuration, even though the Jacobian incorrectly says we're in a singularity. So we summarize our findings by instructing developers of kinematically redundant parallel mechanisms, especially those with non-serially connected actuators, to use non-Jacobian based methods of of path planning and singularity analysis. And for those interested in pursuing this, we've recently proposed the geometric method of singularity analysis, which does not exhibit the issues discussed in this presentation. And the reference for this work can be seen on the slide right now. Thank you very much for listening.